Okay, welcome to the second lesson in our series of renal physiology lectures. This one is on renal blood flow, filtration, and clearance. So we're going to concentrate mostly on the glomerulus and how GFR is regulated, and then we're going to talk about the concept of clearance, which is how renal physiologists and really renal doctors, talk about how they measure kidney function, okay? So the kidney, how it handles substances is really interesting. There's an enormous amount of energy utilized by the kidney to reabsorb substances from the body. So you're filtering them, and then you're really handling them so that in a lot of the cases, not always, but a lot of the cases what you're doing is you're minimizing the loss of that substance. So let's take water, which I've highlighted here. Typically, you'll filter 180 liters of water per day in your kidneys. Humongous amount. But you'll usually urinate only about 1.5 liters, which means that 78.5 liters is being reabsorbed by your kidneys, by your bodies, and returned to the body. So that's 99.2% reabsorbed. So this is the amount that's filtered, which is what we're going to concentrate on in the first part of the lesson today. Bear in mind that a lot of the nuts and bolts of the function have to do with reabsorption, and that goes for maybe the majority of the substances. Here's sodium, millimolar per day filtered, 25,000 millimolar per day. The amount that you urinate, about 150. So that's a humongous reabsorption of sodium and chloride in your body. Chloride the same way, bicarb the same way. 4,500, you're only excreting about 2 millimolar per day. So glucose almost entirely reabsorbed. So under normal conditions. So this happens through this process that we described in the last lecture, where you're filtering, which is the first step. Then you're reabsorbing. In the case of these materials, you're primarily reabsorbing the materials, that is transporting the materials from the renal tubular fluid back into the body, into the plasma. Or in some cases, you secrete substances. You transport those substances from the plasma or the interstitium into the renal tubule so that you can actually excrete even more than you've filtered. But filtration is the first step. Bear in mind, it's only the first step. And most substances are not just filtered, they're also either reabsorbed and or secreted. But nevertheless, filtration is the first step, okay? So a few numbers to remember in terms of renal function here. The renal blood flow is about 1.1 liter per minute, so you guys know if cardiac output is 5 liters per minute, 1.1, roughly 20 to 25% of the renal blood flow goes to the kidneys, and of that, 625 mils per minute is plasma, and that's easy to calculate. If 43% of your blood is red blood cells, then 57% is plasma. So this blood volume per minute times 57% gives you the plasma flow. The glomerular filtration rate is 125 milliliters per minute, and that is 20% of 625. So the filtration fraction, the GFR over the renal plasma flow is 20%. That means 20% of all the plasma that enters the glomerulus is filtered into the renal tubule, into Bowman's capsule in the renal tubule, okay? The urine flow rate, about 1 milliliter per minute. That's what we say is normal, but do bear in mind that varies tremendously depending upon things like how much water you're consuming. Remember that number, but don't take it too seriously. All these numbers sort of vary a little bit. This one varies a lot, okay? And one more thing to bear in mind, we talk about this filtration fraction, 20% of the plasma actually being filtered. If any substance in that plasma is freely filtered as well, that is, it gets through the 3 barriers that we talked about in the last lesson, that means that 20% of that substance is filtered as well. So if you've got So bear that in mind. You're not just filtering water, you're filtering anything that goes through with that water that can be freely filtered in the glomerulus, okay? So when we talk about the filtration of substances, we're not just talking about filtration fraction, we're not just talking about the water, we're talking about anything that goes through with the water. Let's talk about the conditions in that glomerular capillary. On the left here, this should be a familiar diagram to you guys. This is a typical capillary in the body. And so this is the arterial side, this is the venous side. Hydrostatic pressure is high on this side. So we have high hydrostatic pressure pushing water out across the capillary wall. And that is opposed by the high osmolarity in the capillary due to the fact that you have plasma proteins in there that can't get across the capillary wall. We have a special name for that. It's called oncotic pressure. And that is drawing fluid back in. But on balance, because the hydrostatic pressure in the capillary is really high, we're shoving a lot more water out than we're reabsorbing on the arterial end. And then, because there's resistance to flow across this capillary, the hydrostatic pressure drops. You have lower hydrostatic pressure on this end, and now the filtration has gone down. So the reabsorption, that is the drawing of the fluid back into the capillary by the osmolarity in the capillary, exceeds the filtration because the hydrostatic pressure of the capillary is dropped, and now you have net reabsorption on the venous end of this capillary. And on balance, in a normal capillary, filtration overall exceeds reabsorption by a little bit, and that's how you form lymph. Well, the same concepts apply to the glomerulus, but with a much different result. And there are a variety of reasons for this. First of all, notice the differences between these two. The first big difference you'll notice is that you've got filtration all along the length of this capillary. So this is net filtration. That is, you've got water being shoved out in the glomerulus, and it's never reabsorbed. There's never a net reabsorption like there is on the venous end of this capillary. You get filtration all along the capillary. So you've got blood entering through the afferent arteriole, it's exiting through the efferent arteriole, and everywhere in between in those glomerular capillaries, you've got filtration, okay? No net reabsorption, all right? So what are the reasons for that? Well, the biggest reason is because the glomerular capillary pressure is much higher than the capillary pressure in a normal capillary. Here, we're averaging about 25 millimeters of mercury. Hydrostatic pressure in the capillary, if you average these values, you get 25. We did that calculation in the hemodynamics computer program. Here, it's a constant of 55 millimeters of mercury, so that's 30 millimeters of mercury higher than a normal capillary, and that is shoving fluid out. Hydrostatic pressure in the capillary, pushing fluid out, causing filtration. Okay? If you're wondering the reason for that, it's because the afferent arteriole is a lot larger than the efferent, so you've got a big hose with blood flowing in, and then you've got a small hose with blood flowing out. So this is reasonably high resistance on the efferent end, and you've got high pressure upstream of that. It's like kicking a hose. Pressure upstream is high, pressure downstream is low, okay? So you have reasonably high pressure due to that, okay? Notice that the glomerular capillary hydrostatic pressure is constant, whereas here, the hydrostatic pressure is dropping from arterial end to venous end. It's constant here, and that's because the glomerular capillaries have relatively low resistance, at least relative to a normal capillary. So without high resistance, you don't have a big pressure drop. You don't need a big delta P to drive flow. And so the pressure is relatively constant, okay? You have an colloid oncotic pressure. So just like you have proteins in the capillary here that are drawing water back in, you have proteins in the glomerular capillaries that can't cross the wall of glomerular capillaries. We went through that barrier in the last lesson. And so the osmolarity is higher in the capillary than it is in bone and space. So you do have some reabsorption taking place. It's never net reabsorption. It never exceeds filtration, but it's happening. And you'll notice that the oncotic pressure is relatively stable here, and that's because you're not moving that much water. But here, you're filtering a lot of water. And so as you filter the water, as you go through the glomerular capillaries, the amount of water in the capillary actually is reduced. And so the concentration of all the proteins, the osmolarity actually rises as you go from where your blood enters to where your blood leaves. And so you actually have a rise in the colloid osmotic pressure in the capillary, as opposed to it being stable and relatively constant in a normal capillary. Okay? And the last thing you'll notice is that the hydrostatic pressure in Bowman's space is pretty low here. Okay? So you know that the pressure in the capillary is shoving water out, and it's dependent upon the gradient, the pressure gradient across that wall. That is the pressure in the capillary minus the pressure in the tissues. That's what's driving filtration here. Pressure in the capillary minus pressure in the tissues. Here, the pressure in Bowman's space is the pressure in the tissues. That's the pressure that you're pushing against when you filter the water. And that pressure is relatively low. So you're always filtering because this is always a lot higher than this, okay? So let's take a look at this a little bit more numerically. Here is the equation that we're dealing with. And don't let this fool you. It's basically a rearrangement of the same equation that we were using for a normal capillary. Where you had filtration, it's pressure in the capillary minus pressure in the tissues, and that was opposed by reabsorption, which is oncotic pressure in the capillary minus oncotic pressure in the tissues. This is just a rearrangement of that equation, okay? So we have pressure in the capillary driving filtration, glomerular capillary pressure, and that's opposed by the pressure in Bowman's space, okay? And it's opposed by the oncotic pressure in the glomerular capillary, which is the tendency of that capillary to draw water back into the capillary. And there is no oncotic pressure in Bowman's space because it's so low that it drops out of the equation, okay? So this is our driving force for filtration, and this is what opposes it. The pressure in Bowman's space, the oncotic pressure in glomerular capillary, which is drawing water back in, okay? So if I have a glomerular capillary pressure of 55, I can subtract the pressure in Bowman's space, 15, okay? And that's my net driving force for filtration. And it's also opposed by reabsorption, where I'm reabsorbing fluid because my osmolarity is higher here, and I have what's known as a oncotic pressure of 30. Okay, so 55 minus 30 minus 15 gives me a net driving force for filtration of 10 millimeters of mercury. So that means I'm always filtering, and this is the driving force. This is what drives that filtration, and it's mostly because of this high capillary pressure in the glomerulus. Okay, so that's our driving force. Of course, that's not the only thing that determines GFR. The other things are all sort of like conglomerated into what's known as the filtration coefficient, KF here. That is a coefficient which represents, number one, the permeability of the membranes to the fluid. So the more water, the more permeable the membrane is to water, and the substances that go with it. The higher the permeability, the higher the KF, and the more the glomerular filtration rate. And the higher the surface area of exchange, the higher KF and the higher the GFR. So you'll remember that I showed you the glomerular capillaries, they enter and they branch and they coil inside that Bowman's capsule. And that coiling and that branching increases the surface area for exchange of water, for filtration. And the more surface area you have, the more the GFR is, the higher the GFR can be, okay? So the higher the KF and the higher the GFR, all right? All right, so why learn this? Well, it turns out that many, or at least most, if not all, of the diseases that you're going to learn, anything that affects the GFR affects one of these two terms somehow. So let's look at a kidney stone. you've got this kidney stone in there, and it's obstructing fluid flow in the renal tubules, in the kidney basically, and it's backing up. The fluid's backing up, so your pressure in your Bowman space increases, the hydrostatic pressure, and if that increases, then it opposes filtration and you get less GFR. If you have renal artery stenosis, so your afferent capillary is stenosed and the lumen is decreased, you have a higher resistance to flow, resistance like kinking a hose. The pressure downstream goes down, that means the pressure in the glomerular capillaries goes down, and that reduces GFR. Okay, so that reduces your net filtration pressure. Nephritic disease will reduce the number of working nephrons, okay? And it'll also decrease the surface area of filtration and reduce GFR. That's reducing KF in both cases, okay? Sympathetic stimulation will constrict your afferent arterial diameter. Excuse me, that will decrease the hydrostatic pressure in the glomerulus. That will decrease your net filtration pressure, okay? And don't forget the mesangial cells are there. They'll contract, and they will actually decrease the available surface area for filtration, and they'll decrease GFR. So that decreases KF as well. Starvation makes plasma proteins go away, like albumin. That reduces the oncotic pressure in the capillary, and so you actually get an increase in GFR with that, because you've got less water being reabsorbed back into the capillaries in the glomerulus. And finally, if your blood pressure increases or decreases, that will increase or decrease the hydrostatic pressure in the glomerulus, and that will increase or decrease GFR by altering net filtration pressure. Okay? So, that's how your GFR can vary. Let's talk a little bit about what your body does to keep GFR more or less constant. Okay? And it does this through a process called autoregulation. Now, autoregulation is something you find in the arterioles and the arteries pretty much all throughout the body, okay? But it's really, really exaggerated in the kidney. And what this is, it's a process. This is an increase in blood pressure. And as you might expect, as blood pressure increases, you increase the pressure in the glomerular capillaries, you increase GFR, and so GFR, renal blood flow goes up because your pressure is up. GFR goes up because your glomerular capillary pressure is up. And then look what happens. You hit about 80 millimeters of mercury, which means you're just starting to enter into the normal range for arterial blood pressure. And all of a sudden, the GFR and the renal blood flow are both constant. And this is due to the autoregulation. And what happens is, if you as the pressure goes up beyond this point, the resistance increases. The smooth muscle in the afferent arteriole, and to a certain extent the efferent, will actually start to contract in response to the increased pressure in the lumen, presumably due to stretch. The mechanism's a little hazy, not very well known. It seems like the smooth muscle depolarizes. It allows more calcium to come in, but really not too sure about the mechanism on that. But nevertheless, this is what happens. The pressure continues to go up, but instead of the flow continuing to go up, it becomes steady because you get this constriction of the arterioles that increases resistance to flow. So flow is equal to delta P over resistance. The delta P is going up. As the pressure goes up, the resistance goes up with it because of this autoregulation. Okay, and so you end up with a constant flow until you finally hit about 180 millimeters of mercury, and then the flow starts to rise again because you've pretty much overwhelmed the system at that point. Okay, so this happens through two mechanisms. The myogenic mechanism we've kind of already described, and this is how normal arterioles sort of like have this autoregulation. And that's a response of the smooth muscle to stretch, just like I said a minute ago. And you get this constriction in response to that, presumably due to activation of calcium channels and increase in the voltage. You also have this through the action of the juxtaglomerular apparatus. And I described this in the last video, but as a brief review, this is the apparatus. Your afferent arteriole and your efferent arteriole are very close to the distal convoluted tubule. And if you increase GFR, you increase the fluid flow past this macula densa, it senses this increased fluid flow through a mechanism that's pretty hazy. Seems to have something to do with sodium and chloride and the rate at which it arrives here. But nevertheless, the macula densa senses that increase and secretes a vasoconstrictor, ATP or adenosine or something related to that, something related to adenosine. And that vasoconstrictor will cause these arterioles, primarily the afferent arteriole, to constrict. And so that will regulate glomerular pressure by regulating glomerular plasma flow or blood flow. Okay? It'll cut blood flow down and cut pressure down. So, and that will reduce your GFR in the face of a higher blood pressure. Okay? So I went through that in the last lecture, lesson. I'm not going to talk about a lot here, but nevertheless, that contributes to this autoregulation of the kidney as well, and that makes this a particularly powerful mechanism in the kidney, because this is a mechanism that other capillaries throughout the body don't have. Okay, so that's autoregulation. Bear in mind, there you go, here's our sodium and chloride. And bear in mind that the granular cells are not involved in tubulo-glomerular feedback. They secrete renin, and we'll talk about that in a later lesson. Okay, but they're illustrated here as well. And also bear in mind that extrinsic factors will override this. So if I get an increase in sympathetic tone, let's say, that will decrease blood flow to the kidney. That will override this autoregulation mechanism. Your GFR actually drop. Okay, so bear that in mind as well. This is in the absence of extrinsic neural innervation. In fact, you can cut the kidney out, cut the nerves out. And in the case of the myogenic mechanism, you can actually denude you can isolate the arterioles and denude them of endothelium, and we'll actually do this. Okay, so this is strictly kidney property of the kidney. Okay, having nothing to do with autonomic regulation, but autonomic regulation will override it. Okay, so that's all I've got for the GFR and regulation thereof. So I'll conclude this part of the lesson, and we'll move on to the concept of clearance in the next video. Thank you.